So hello and welcome student to this lecture, and this is course number MA412 linear algebra, and this is lecture number 38. Okay, so now recall that in our last lecture we discussed about symmetric bilinear forms. Symmetric bilinear forms. Okay, and then we discuss about diagonalization of symmetric bilinear forms. What is that? So if there exists a basis such that the matrix representation of the symmetric bilinear form is diagonal matrix, then we call that bilinear form is diagonalizable. Okay, and then we immediately prove that if you have a symmetric bilinear forms, suppose you have a finite vector space and a bilinear form which is diagonalizable, then it is also symmetric. That is proved. And we showed that convergence is not true in general. For example, if you have a vector space over a field F whose characteristic is 2, then this is not true actually. We give an example. But then what happens if the characteristics of the field is not true? In that case, actually, the converse is true. Converse of the theorem that for finite-dimensional vector space, symmetric bilinear forms are diagonalizable, bilinear forms are equivalent. Okay, when the characteristic of the field is not true, not equal to 2. Okay, and so we will prove that theorem today. And before that, we need to describe one more observation. You can say the lemma. We start with the lemma. Okay, so what is the lemma tells us? So suppose I have a bilinear forms on any vector space whose characteristic is not equal to 2. So let V be a vector space over F such that the characteristics, I hope we know already what is the meaning of characteristics of a field. Okay, is not equal to 2. Okay, so what does that mean? That means that this means 1 plus 1 cannot be 0. So it cannot be 0. Those field. Okay, so characteristics not equal to 2, and you choose a bilinear forms or other symmetric bilinear forms, and H be a symmetric. I need something say non-zero also, so non-zero, we cannot be identically 0. Symmetric bilinear forms suppose. Okay, so this is given to us. So I have a vector space over a field whose characteristic is not equal to 2, and I have a non-zero symmetric bilinear forms. With this condition, we can find out the vector. Then there exists a vector, say, rather I should say non-zero vector. Obviously, for the vector, it is always trivial, right? There is a non-zero vector x belongs to V, such that the value that H takes on x and x equal not equal to 0. Obviously, x has to be non-zero. If x equal to 0, is always 0, right? So you should have you can find a non-zero vector B such that H does not vanish on if you apply xx. Okay, so H is non-zero means you can find out a vector such two vectors, say u and v, such that H, u and v not equal to 0, right? But you don't know whether they are same or not, u and v. Okay, so how do you prove it? So proof. So what is given to us? It is given that H is a symmetric bilinear forms and over a field over a vector space V, and the field of the vector space has characteristics not equal to 2. The characteristic can be anything other than 2. Okay, this is given. So as H is non-zero, non-identity is 0, there exists two vector, so U and V belongs to V such that what happens such that H of U comma V not equal to 0, right? That is the meaning of non-zero. Otherwise, if it is otherwise for every such vector U V is 0, then it is 0 vector, right? So now the question is that what happens if U and VB, any of those things is 0 under H, right? So if either H U equal to 0 or H non-zero, obviously, or H VB is non-zero, then we are done, right? Then that is the proof. Then we are done. Okay. So now assume that both HU and HVB are 0. Then what happened? Okay. So otherwise, let both this HUU and HVB both are 0. If one is non-zero, then we can choose my x equal to that. Otherwise, both are 0. In this case, choose my vector x equal to say u plus v. And if I choose this, then what happens? Then h of xx, by definition, this is h of u plus v, right? And the property of bilinear form tells you that this is hu plus huv plus hvu plus HVV, but it is 2 or 0, you know that, right? So we have, okay, so let me first write down HUV plus HVU, right? But again, we know that H is symmetric, so HUV, HVU is same, right? So this is 2 times HUV and H is symmetric. Because, right? And now see, we find out, so we know that this is non-zero because H is a non-zero vector, a non-zero bilinear form, so we can find out UV says that this is non-zero, right? Now because this factor is non-zero, and if you multiply by 2, it has to be non-zero because the characteristic is non-zero, as this UV is not equal to 0 and characteristics of the field F is not equal to 2. If characteristics of the field F equal to 2, then this product, 2 into this will become vanish, like this will become 0. Okay. So that is the proof. So in any case, whenever the characteristics of the field is not equal to 2, you can find out a vector such that hxx will be always non-zero for any symmetric bilinear forms. Okay. Now with the help of this lemma, we are going to prove the converse of the theorem what we discussed last time. So we proved that on finite dimensional vector space, if we have a bilinear form which is diagonalizable, then that is then also it's symmetric, right? Now we will prove the converse part. If it is symmetric, then it's diagonalizable under the condition that characteristics of the field is not equal to 2. So what is our theorem statement? So theorem. So let V be a finite dimensional vector space over F such that characteristics of if not equal to 2. Okay, this is given to me. Then in this case, every symmetric bilinear form on V is actually diagonalizable. Okay, so what does that mean? That means you can find out a basis with respect to which the matrix representation of that symmetric bilinear form H is actually the diagonal matrix. Like that psi of H with respect to beta is a diagonal matrix, right? That we need to prove. Okay, so obviously the dimension is finite, then see, so we will use that induction on the, okay, so we will use mathematical induction on this dimension of V, right? And obviously if this is 1, then this is obvious, right? And then there is nothing to prove. It's obvious because this is matrix will be single entry, is diagonal, right? Nothing to prove. Okay, now we'll use induction hypothesis. So assume that this is our induction hypothesis. Assume that the above statement means the theorem statement. Okay, statement is true for any vector space of dimension less than n. Okay, now we start with dimension of, next we start with dimension of V is n. So this is our starting point now. So now we'll show that inside V we can do the same thing. Okay, so what does that mean? That means first we will find out the subspace of V whose dimension is less than n. Then we will use the mathematical induction or that induction hypothesis on that, and then we will extend it. Okay, so dimension of n equal to V equal to n is given, and also it is given that also I have to choose that V is non-zero. So if H belongs to say BV is a zero bilinear form, then it's obvious, right? Zero bilinear, because then the matrix will be zero matrix which is diagonal, right? Linear form, then the theorem is trivial. Right? So what does it, so we assume, so thus assume that H is not identically zero. Okay, it's non-zero. Now from the previous lemma, what do you know? So then by previous lemma, there exists x belongs to V, a vector such that H xx not equal to 0, right? This one tells you that whenever you have a symmetric bilinear form which is not identically 0, then this done. Okay, so yeah, so the symmetric is given. Okay, and the symmetric is given. Remember, symmetry is given. We need to prove this is diagonalizable. Okay. So h of x is not equal to 0. Okay. So this is the vector that we need to use it. So with respect to this vector, so we will define the map L of x from V to is a linear functional on V. And what is the map? So we define it by L of x of y for any vector y. It is h of xy, right? For all y belongs to V. It's bilinear form, so this is the element of f. Okay, and so obviously this is linear, and that already we proved in one of the last lectures. So this is linear, not only that, you check that Lx on x, it is h of x comma x, which is non-zero. So Lx is also non-zero. So Lx is a non-zero linear functional. Okay, this is clear. So non-zero linear functionals, what does that mean? That means the range of Lx has to be full f, and hence the rank will be 1. So thus rank of this Lx equal to 1, right? It's clear because this is non-zero, and hence so this is non-zero. So this Lx will be, there will be non-zero element inside f. So this is one-dimensional, the image, and hence the rank will be 1. And so you can have the nullity. You know the rank nullity theorem, right? So nullity of Lx will be the dimension of V minus rank. So this is n minus 1, right? N is the dimension of V, and the nullity will be this, right? So what does that mean? That means the dimension of the null space of Lx is n minus 1. Okay, but the null space is actually subspace of, right? So null space of Lx is the proper subset of V, right? And V is dimension n, this is dimension n minus 1. So null space has a dimension n minus 1 means what? So you can use the induction hypothesis. So we will use so thus using induction hypothesis, what does hypothesis suggest? That whenever we have vector space whose dimension is less than n, so we can do something, right? So we will use the induction hypothesis, and on the map, so you restrict h on this Lx. Let me write down the name, say n probably. So this is, maybe we can write down this is by n. This will reduce our work. N. Whatever. So this map is from Lx to f. That's just the map. So you are restricting h on Lx. Okay, the null space. So this map is what? So this map will be obviously on this. So this h restriction n is symmetric. Obviously it has to be symmetric because restriction of symmetric will be symmetric, right? Symmetric bilinear form on n and dimension of n is less than dimension of v, right? So what does that mean? That means H restriction n is diagonalizable using induction hypothesis, right? So what does that mean? That means that means there exists a basis. There exists a basis, say v1, v2, and say vn minus 1 of null space, which is I am writing ns, such that the matrix representation of this psi with respect to, okay, let me write down the name, maybe something gamma. With respect to this gamma of this map, this is a diagonal matrix, right? So this is diagonal D. Diagonal. It is symmetric and also diagonal. So what does that mean? That means that is so this matrix are what? This matrix is so when you're restricting, that means you're finding H, this B, I, V, J. So these are the entries of the matrix, right? Or rather you can say Hn, no problem. But these entries is diagonal and also is symmetric. So there is only option, this has to be 0 for all I not equal to j. Okay, when I equal to j, then I don't know, but at least when I not equal to j, I know that this has to be 0 because this will give a diagonal matrix, right? Clear? This one is clear? Okay. So now, okay. Now you choose a. So now consider you this new basis. So this is basis of V. So you have x1, v1, v2, everything is there. This is basis for null space of Lx of dimension n-1. Now you are also adding x. So this is a basis. It's a basis of V, right? Why this is a V? Because x is not inside null space, because L of x is C. I think we have shown here somewhere. Yes, yeah. So when we evaluate Lx at x, then it is non-zero, right? So x cannot be inside the null space of Lx, and hence you can add. So this will be linearly independent with this v1, v2, vn minus 1, and if we attach that thing, that will be linearly independent set of cardinality n, and hence this will form the basis of V as dimension n, right? This is clear. So the answer of this is a basis of V, and with respect to this basis, what happens? So with respect to this basis, when you calculate the psi of this, of n, of h, then what happens? You see till v1, v2, vn minus 1, each vi is 0, that you already find out from induction hypothesis. Only thing is that you need to find out what is the value with respect to x. Okay, now I am claiming that this is also diagonal, some d dashed. And so what is this d dash? So d dash is nothing but you have d here sitting, and the last term, this can be non-zero, and this will be of 0. Why this will be 0? These are nothing but the evaluation of x with respect to x, right? As so this is true as you see each x comma vi, this is L of x of vi, but vi's are in the null space of x, so this is 0 for all I equal to 1 to up to n minus 1, right? And because h is symmetric, so h of vi of x equal to h of x of bi, they are 0, right? And these are the nothing but elements of this portion and this portion. Okay, so these are all are 0, and hence thus psi bh is a diagonal matrix. And hence H is diagonalizable. Diagonalizable. Okay, so this proves that whenever you have a symmetric matrix on a finite dimensional vector space over a field F whose characteristic is not equal to 2, then this bilinear symmetric these bilinear forms are also diagonalizable. These symmetric bilinear forms are also diagonalizable. Okay, other portion we already proved that is true always. Okay, and what is the immediate corollary? So immediate corollary, you can say that so what is the matrix form of that? So if you start with a matrix, so maybe you have a matrix, say in present matrix over field F and characteristic of F not equal to 2, then what you can say? Then you can say that the symmetric, if A is symmetric matrix, then A is diagonalizable. That means A is congruent to other I should say A is congruent to, not diagonalizable, congruent to a diagonal matrix. Okay. So this is the corollary, that's straightforward from the above theorem, because whenever you have a matrix like this, you can attach a symmetric bilinear forms, symmetric bilinear forms which is on financial product space in vector space characteristic 2 are diagonalizable, and hence A is congruent to that. So you can find out another basis with respect to that, it is diagonal matrix, right? So this is obvious. Okay, so now we are going to discuss one more new concept attached with the symmetric bilinear forms, and then we will stop our lecture today. And this is called quadratic forms. Quadratic forms. So what is that? So whenever you have a symmetric bilinear forms, then you can attach a quadratic forms. So let me write down properly definition. So let V be a vector space over field F. Okay, and so a map K from V to F is said to be a quadratic forms form if there exists a symmetric bilinear form, H belongs to BV such that what happens is that K of X has to be H of XX for all vector X belongs to V. Okay, then we say that K is a quadratic form. So quadratic forms are kind of evolution at a symmetric bilinear form. Okay, and so what does that mean? That means quadratic forms are actually determined by the symmetric bilinear forms. And converse is also true if the characteristic of the field is not equal to 0. So what does that mean? That means if you have a quadratic form, then also you can define a symmetric bilinear form. So this you can recover actually bilinear forms that from the symmetric from the quadratic forms. So And if obviously that f is not characteristic 2, so if characteristics of the field is not equal to 2, then what you can do, then actually this space of quadratic forms on V and space of bilinear forms, so this is by BV, rather symmetric bilinear forms, so is SBV. SBV is a subspace of all the bilinear forms which is symmetric. Okay, so this is symmetric bilinear forms. So these two spaces are actually one-to-one correspondent. I mean, there is a bijective correspondence between these two spaces, right? So if you have H there, then you attach K by K of X going to XX, right? And if you have K here, then you attach H of XY equal to half of K X plus Y minus Kx Ky. This is the relationship between, this is the bijective correspondence. So there is a map H goes to Kx and then from here K to H. Okay, so if this is characteristic not equal to 2, then quadratic forms are bijectively corresponding to the symmetric bilinear forms, right? Okay, so maybe we can give an example. So let us think, for example, suppose we have so let me give an example for say for v equals R3. So you have three vectors. I mean basis of three vectors and three coordinates. Okay, 1 and 3, and then you choose your say x, which is say x1, x2, x3 in R3, and then you can define say so my kx. So generally in this case kx is defined by the polynomial or whatever you have polynomial in three variables, so x1, x2, x3. So what is the x is a vector, right? So x is this. Okay, so I wrote already. This is you can define by anything, right? Like t on x1 square plus say 2 x2 square plus 3 x3 square plus something say 4 x1 x2 minus 6 x1 x3, something like that. Okay, so obviously one can ask what is the bilinear form here, right? So the bilinear forms corresponding to this is the matrix. So you need to find out the matrix first. So here you see that because this is symmetric, so you need to, so this has to be the half, right? So this is 1, 2, 3, x1, 1, 1, 2, so this is 2, 2, and then 1, 3 is 6, so this is minus 3, and minus 3, and then 2, 3, 0, 0, right? There is no term x2, x3, right? So this is the matrix dependence of actually these quadratic forms, and you can define the bilinear forms. So the bilinear forms is what this is. The quadratic form you can write down actually if x1, x2, x3 in terms of this x1, x2, x3 transpose into the matrix A into x1, x2, x3. Okay. Yeah. So it's clear. So this is for the matrix are what? The matrix actually. So in general you can write down if the matrix of this bilinear form is A. So suppose H is so this is a correspondent k equals to H. K is the quadratic form, H is the symmetric bilinear forms, and then you can find out the basis such that the matrix will be of the form, say, Aij. How Aij looks like? So Aij's are nothing but these Aij's are okay. So I should suppose originally this is Aij, and in general. So the original matrix I should say, but here let me write down. Okay, I have to say something like this. So the symmetric. So what does that mean? That means the original matrix, whatever you write down, these diagonals are A11, A12, and 3. But other than the diagonals, other elements are half of those things, right? So it is kind of, so A11, A12, and so A22, and so on, ANN. But here half of A12 and half of A21, because these two are symmetric. When you multiply, you will have full, right? So that's why I wrote this matrix C. So this is corresponding to the 1th row and 2nd column entry 4. So you have, this is half of that, so on. Okay. So so this is the way to find out the matrix of the quadratic forms. Okay, so now let us discuss how the quadratic forms. So the quadratic forms on reals are more important, so we will discuss that. And for real numbers, we know that symmetric matrices are actually not only diagonalizable, is also something called orthogonal diagonalizable. So that means you can find out the orthogonal matrix, which actually takes the symmetric matrix to the diagonal matrix. Okay, so that is the meaning of orthogonal diagonalizable. And in this case, you can say many things on symmetric bilinear forms, and similarly you can say about quadratic forms. So in this case, so let us find out what happened for vector space over reals. Okay, so theorem. So maybe we can choose inner product space. Okay, so let V be a finite dimensional real inner product space. Suppose this is given to us, and we have a symmetric bilinear forms on V. H be a symmetric bilinear form on V, and then actually H is not only diagonalizable, H is obviously diagonalizable, but it's something more. So you can find out the orthogonal or other orthogonal basis such that the diagonal, the matrix representation of H is actually diagonal matrix. So you can take a diagonal with the orthogonal basis, a very stronger condition. Okay, then there exists an orthogonal matrix, or rather there exists an orthogonal basis orthonormal basis B of B such that psi of B of H is a diagonal matrix. Okay, so this is a very strong condition for real inner product space, and the proof is also not difficult. So this is following from the fact that any matrix which is over R and symmetric, they are orthogonally diagonalizable, right? Is that property right? We will choose. So because given that V is finite on the inner product space, so always you can find out the non-orthogonal basis, right? So let you start say something beta dash is something like V1, V2, Vn be a or an orthogonal basis, orthonormal. So you can choose anyway, always exists, right? Basis of V. Okay, so you choose anything, and then let the matrix of H with respect to this basis be say something, say A. Suppose this is A, because A is symmetric bilinear forms, so then obviously A has to be symmetric. A is a symmetric matrix, right? Symmetric matrix as H is a symmetric bilinear form. Bilinear form. Okay, but A is a real symmetric matrix because the vector space is over R, right? So A is a real symmetric matrix, so A can be orthogonally diagonalizable, right? As A is a real symmetric matrix. A can be orthogonally diagonalizable, right? So that is, there exists an orthogonal matrix. So Q, so maybe is of the form Qij such that, so you can write down that Q transpose. See, orthogonal means, real orthogonal means Q transpose equal to identity, and hence Q transpose equal to Q inverse. Okay, so Q transpose A Q, it has to be diagonal matrix D, right? So D diagonal. So Q inverse AQ is a diagonal matrix, and now obviously so Q so what is the advantage here? Here A is both similar to diagonal matrix and also congruent to. So D A is also congruent to diagonal matrix, right? So orthogonal real orthogonal matrix, this is the advantage. They are both congruent diagonal levels. So that I am going to use it here. Okay. Now so on the one hand this is diagonal level similar, other hand this is congruent. Now this congruent fact we need to use it, and we use the property what we proved in last lecture. Okay, so now we will define the new basis B, and the elements are say omega 1, omega 2 and so omega n, where this omega j's are summation qij and vi equal to 1 to n. So we define by this identity the dj's are the new elements. So we will prove that Vj's are actually orthonormal vectors. So the proof is easy because you start with let's say Wi. Yeah, so maybe I can write down. Yeah, so maybe Wi, Wj I need to prove. So let me just write down first. In Wi say Q Ki Vk k equal to 1 to n. Okay, and j for j let me write down by summation q r j and vr r equal to 1 to n. Wj equal to qj, right? So this is time variable. Similarly, here k time variable. Now if you do inner product, they will have what? So this is real remember real inner space. So power will be same, right? So it will be double sum k equal to 1 to n qi, and then ri1 equal to 1 to n qrj, and then vk vr, right? And now when r equal to k, only this will survive because it's orthonormal, right? We already choose, remember. So this is orthonormal basis C. So whenever r equal to k, then only this will survive 1, otherwise 0. So when r equal to k, this is what? This is summation k equal to 1 to n and q ki, and this will be q kj, this is 1, right? When r equal to k. So q ki kj, what does that mean? So that means this is actually you can write down the transpose of that, right? So you can write down q transpose ik q kj, right? K equal to 1 to n, and this is the ith row and jth column of this matrix, right? By ith row jth column of this matrix Q is what? This is orthogonal matrix. Okay. So if you have the orthogonal matrix, you know the real orthogonal matrix are so this portion has to be. So there are two options. Whenever I not equal to j, there will be one option. When I equal to j, there will be one option. When I equal to j, this will be 1, and when I not equal to j, this will be 0, right? For real orthogonal matrix, right? Because this is a product of, so this is nothing but q transpose and q. So this is identity, right? So ith row and jth column. So only when I equal to j, it is 1, otherwise it is 0, because this is identity matrix. So this beta is an orthonormal basis of P, such that what happens such that is psi of beta is a diagonal matrix, is a diagonal matrix. Okay, so that is the proof. That is the proof. So you can find out things such as diagonal matrix, and that tells you that I mean that is the theorem we proved. Okay. Now, what is the immediate corollary of this theorem? So immediately, what you can say from this theorem for quadratic form. So you can say that you have a quadratic forms of Induction linear space. So be a finite dimensional real inner product space, and K be a quadratic form quadratic form. So let me write down this symbol KV space of all quadratic. You collect all the quadratic forms. Okay. Okay. So with this case, there exists an orthogonal basis so B of V1, V2, Vn of V. This is the basis for V, and you have scalars, say C1, C2, and say something Cn belongs to. So this is real, remember. So this is element of R. Okay. So this Ci may not be distinct. So it can be C2 can be equal to C3 or C5. Okay, anything. So this can be there such that say if you choose an element of V, say X, and maybe summation Si and Vi with respect to the basis. Okay. If X equal to this, then actually you can write down Kx. Then your quadratic forms will be of this form: summation Ci this Si square I equal to 1 to n. Okay. So what does that mean? That means you can change the basis from there to your orthogonal basis such that so this is orthogonal basis actually. Some X equal to Si Ci. So you can write down the element in terms of orthogonal basis such that whatever the quadratic forms is given to you, that you can change it to the nice form. Why it is nice form? See here, there is no product form here, right? So in the original space, the Kx, whenever you talk about quadratic forms, you will have product, right? Say T1, T2 or X1, X2, X3, right? Here you don't have. This is kind of homogeneous quadratic forms whose product form is not there. So that means corresponding matrix will be diagonal, right? So it's only the diagonal things, and that is obvious because of the previous theorems. Okay, the previous theorem tells you that. Okay, so proof is what? Proof. So so this K is given, so that means there must be a symmetric bilinear form, right? So let K be the symmetric bilinear form, symmetric bilinear form such that K of X equal to is Hxx, right? This is by definition, and because it is symmetric bilinear forms on real vector space, so there exists orthogonal basis. So there exists an orthogonal basis, orthonormal basis, say which is my V1, V2 and Vn, such that the matrix of H will be a diagonal matrix, right? Such that this psi b of H, this will be a diagonal matrix D, and we can write down the diagonal entries are C1, C2 and Cn, other than 0, right? So this Ci may be repeating, so that I told you, this may not be same, may not be distinct, I am not saying. Okay, so this is the matrix representation of H, the symmetric bilinear form with respect to the basis B, and so now you can choose about you choose any vector. So let choose any vector V, and you write down this in terms of the basis vector. Then in terms of this basis vector, this orthogonal basis vector, you write down the X equal to summation, say Si Vi I equal to 1 to n. Okay. Now once you write down this thing, then what you know, then by definition of kx, it has to be h of xx. By h is symmetric bilinear forms, and you know what is the matrix of h. So by a theorem which we proved that every bilinear forms are actually coming from a matrix, right? So this one-to-one corresponding between matrices and bilinear forms for finite dimensional vector space, right? So this will be your the coordinate maps of this S, that x with respect to the basis B, that transpose, and the matrix D is a diagonal matrix, and then coordinate maps Q of beta of x. Okay, the coordinate maps of x is what? This is nothing but this S1. See, with respect to this basis beta 1, what are the coordinates? This is S1, S2, S3, right? This is the coordinate. So you can write down that coordinate with respect to the matrix is nothing but S1, S2, and so on, Sn, right? This is also we can write down phi beta of x, same symbol. Okay, so this is S1, S2, and dot Sn transpose, and then D, and then S1, S2, and Sn, right? And done. So you have a diagonal matrix here, and then you multiply these two things, so it will be nothing but Ci Si square, right? So here is Si here, Si here, I equal to 1 to n. This is the theorem that yes. Where is that statement? Yes. Then you can write down. So you can convert any quadratic forms into a nice forms. Quadratic forms to a suitable quadratic forms where there is no product monomials. Okay. Okay. So maybe I will stop here for today's lecture. Okay.